SwayamPrabha. Digital India. Educated India.
So, welcome back to another lecture on introduction to soft matter, and last time we were discussing a particular sample problem that we have not fully solved, and we were half in the process of solving, and I had asked you to finish off the problem as part of the self work, right. So, now I am going to work out the entire problem, and you can check whether if you have worked out the answers, you can check whether your answers do match with us. So, the particular problem that we had, it involved n number of Kelvin Voigt Meyer bodies in series, and with a final spring in series as well. And we wrote down that the force balance for this again is very straightforward. It boils down to the fact that the forces in all of them are actually equal, and then we wrote down the geometric constraint as well. So, then now we have to write down the individual equations that apply to this case, right. So, let us start with just to simplify our situation, we will just, because this spring stands out, I will just write the spring equation first. Okay. So, the equation of the spring is going to be F naught equal to this E naught into delta x naught. Now, the equation for all the different Kelvin Voigt Meyer bodies, they are going to be all the same, and the force here is going to be given by E 1 eta 1 times the differential operator into delta x 1, and this is going to be continued all the way till all your n elements are complete. Sorry, the subscript here would be capital N d delta x capital N. So, this is all the different equations that are there. Now, let us quickly go back and see what we had first established. We said that the force balance equation says that all the different forces are the same. So, I can actually go ahead and drop all these different subscripts. So, I just go ahead and erase the subscripts, so that we are all left with F on your left hand side. And now, to make these equal, so we want to be able to add all these deformations together. So, we have to find the right factor for all of them. So, what we are going to do is we are going to multiply this entire part by 1 by E naught. So, I want to cancel this part out, and then I am going to multiply it with all these different factors E 1 plus eta 1 d, and this way going all the way till E n plus eta n d. Similarly, for the second case, we are going to multiply by the way, please remember always that when I write it like this, because the equations have become too cumbersome, I do not want to write it on both sides, but here what I am implying is that this factor has to be multiplied on both sides, the left hand side and the right hand side. Just because I am writing it on one side, do not get confused. This is just for the sake of space. So, in this particular case, you already have this factor there. So, we can leave that out, and you can multiply this entire thing with E 2 plus eta 2 d, and going all the way till right. Similarly, for the last case, you can argue that you are going to multiply it with multiply it with, you will start off with the first element and then you will end with n minus 1th element. Okay. Running out of space here. So, we will just make it more compact, E n minus 1 plus eta, actually I am really out of space. Okay. So, I am just going to compress things here. So, we have n minus 1 plus eta n minus 1 into d. So, I hope you can see what I am trying to do. I am trying to ensure that all the delta x's now have the same multiplication coefficient in front of it. So, that I can just go ahead and add. On the left hand side, obviously, you have the same forces. So, you do not have to worry about that. So, in that sense, on your, when you add all this together, what you will end up getting is, on this side is very straightforward. You will have all these different multiplied till the nth factor, right. And for f, you are going to have a situation where you are going to have a polynomial again in D, and this time the highest power of the polynomial is going to be. So, in this case, for example, you see we are going to have n number of, so you will have D n times, right. So, the highest power of D is actually n. Okay. Do not get confused here, because here when you multiply on this side, you will have the highest power as D n minus 1, but the first term itself is going to give you D to the power n. So, the highest power is D to the power n, and let us just quickly check whether we are going to have any term independent of D, and that looks to be true. For example, in the first case you have E1s, all the EIs multiplied, and that will not have any D operator multiplied with it, right. So, here on your left hand side you have now have a polynomial such that so, this has been quite interesting. So, this is the we end the sample problem here, but with this we have seen a number of different examples. We started off with one of the simplest possible viscoelastic models, which was the Maxwell model. Now, I want you to remember one thing. Okay. So, we will just make some important remarks about the kind of models that we have discussed. So, all our discussion was always about one dimensional models, okay. Because we were calculating delta x, you have to remember that the way we formulated the entire model is valid for a one dimensional case. So, all models discussed were for one dimensional or one dimensional cases. Okay. So, if you have to create models for 2D and 3D, they are actually generalizations of this, but this is an important starting point, but these were all one dimensional systems. Okay. Even if you have any number of elements, that does not imply that you have generalized it to other dimensions. We are still subject to the restriction that we are discussing only one dimensional cases, right. Okay. In Maxwell model, so in a sense the viscous part of the Maxwell model is for a Newtonian fluid, in the sense that the viscosity is not shear rate dependent. Okay. So, the viscosity etc. were assumed to be constants at all different shear rates. Okay. So, or maybe I will just reword this sentence here. So, to just write this, so the second point is that the Maxwell model where we discussed, please remember that the constants are actually the E1 and etas are actually constants, right. So, those are not viscosity dependent. Okay. So, in Maxwell model, the viscous part is shear rate independent. Okay. So, eta is not a function of gamma dot. So, while the the Maxwell model does represent a good viscoelastic model, it will not be appropriate if you want to model a shear thinning or shear thickening behavior. Right? Okay. The third important point is, in a Maxwell model, the spring and the dashpot represent phenomenological objects, in the sense that there is no real spring or real dashpot in the system. The spring represents a storage of energy, the dashpot represents a dissipation of energy. They are analogues. Okay. They are analogues derived from the continuum world and being applied to the continuum world. So, microscopic features of a fluid are not taken into account in the model itself. We have not made any assumption, inherent assumption about what the fluid actually looks like at the atomistic scale. So, the molecule, while the continuum approach is nice in a certain sense, that it does not rely necessarily on the microscopic details, it does miss out on some. Right. So, there are later on we will see that or in a more advanced course you will see that these models, there are other models which are better equipped to handle some of the real world fluids. So, all these models used mechanical analogues to model or analogues for characterizing, or all these models use mechanical analogues for characterizing material response. And we saw that for complicated systems you can end up having different type of characteristic time scales. So, there are time scales associated with the relaxation phenomena, where we then call it the relaxation time scales, and then there are characteristic time scales associated with the creep phenomena, where we would call them the retardation time scales. Okay. So, note we saw different types of time scales, characteristic time scales, sorry. So, I will add that characteristic time scales. Okay. So, now that this, so we saw that for an n body system, for example, a Maxwellian model where you have n number of elements, maybe if in one case we replaced, we said that the viscosity tends to infinity, and then we saw that there will be n number of whatever is the order of the polynomial, that many number of characteristic time scales will be there, right. So, there exists a generalization of this idea where we have a discrete set of characteristic time scales. We say that in a more general sense, it is possible that a fluid can have an entire spectrum of time scales. So, the time scales themselves go from a discrete variable to a continuous variable. Okay. So, generalization of these ideas of the time scale ideas introduces a continuous distribution of relaxation times. Okay. And in that kind of a situation, you will write it as this g t can be written as some g naught plus 0 to infinity some another function g lambda. Okay. This is please note that this is a different function e to the power minus t by lambda d lambda. And in this case g lambda is also called the distribution of relaxation functions. It is customary in polymer science and engineering to not use a linear scale, but to use a logarithmic scale. And in that case what we have to do is we have to introduce another variable, which is now so this d lambda is the lambda is the time variable, the characteristic time scale associated here, and you can now take the logarithmic of the logarithm of lambda, and let us say y is that variable. So, this implies that your dy is equal to d lambda by lambda. So, if your previous expression now, if you substitute it there, this will become g naught plus integral 0 to infinity g lambda, and now I am going to transform it into the derivative. Instead of being the derivative of lambda, I want to take the derivative of lambda log of lambda, right. So, then I will just transform the variable here, this is dy, or you can instead of dy you can just write log of lambda, either way it is the same thing. And now this particular function is usually denoted by h, or it is also called. Okay. So, this particular function now g lambda lambda is regarded as another function, and this is now called the relaxation spectrum. So, this is nothing but now a function of a slightly different function derived from the previous case. And similarly, for creep, this generalization leads to an expression of the form where j t becomes some 1 by some constant plus 0 to infinity c tau 1 minus e to the power. So, I am just using a different variable here because I have used lambda just to differentiate the two cases, and d log of tau. Okay. And then this particular function here, this is also called the retardation spectrum. Now, once you go into this retardation spectrum, into this generalization, you can no longer use a finite combination of springs and dashpots to model this kind of a system. Okay. So, This is, so we have seen that we started with a one dimensional system and we went towards, we started off with a very simple system and we went on and made the system more and more complicated by adding more elements. And finally, we came up with an idea of how the relaxation time scale itself varies and depends on a number of time scale, has a number of characteristic time scales built into it, and we finally generalized the idea of the characteristic time scale to get this idea of the relaxation and the retardation spectrums. Okay. So, at this point what I would like to do is I would like to introduce another important principle called the Boltzmann superposition principle. Okay. Now, this particular definition or this particular variation of the Boltzmann superposition principle is taken from the book Mechanical Properties of Solid Polymers by I.M. Ward, which is a John Wiley and Sons publication. The particular edition that I have is from 1983. And here what this book says is that the Boltzmann's proposition was that, and that the creep in a specimen is a function of the entire loading history. That is number one. Okay. So, you can see that Boltzmann is bringing in the idea of memory right here, okay, that you have memory built into the system. It is very elegantly put. And then at each loading step makes an independent contribution to the final deformation, and that the final deformation can be obtained by the simple addition of each contribution. Okay. So, this is basically a mathematical statement that which we have sort of already discussed in the case of the superposition of responses, and we will just reformulate that for the case of Boltzmann. Because we will see that it leads to another interesting generalization. Okay. So, that is why I am discussing it again. So, let us say, so I am just trying to draw what was said in words there. So, let us say you have the stress on one axis and this is your input and you are measuring the response. So, response is going to be the strain, right, and these are the time axes. Let us say you have different points which will denote as tau 1, tau 2, tau 3, etc. And there are too many points. Okay. So, let us say the stress is such that it is being applied such that you are applying some unit stress between this interval, and the next interval you are increasing it to some other value and so on. Okay. So, if we have to consider the creep response here, the creep response will look as if right now it is 0 and here it will increase because of the stress that you have put. Then it is going to increase again. Now, it is going to be a slightly different function because you have changed your stress. So, there is another delta sigma that is you have added, and then you have added another delta sigma here. So, it will change. Okay. If you have to put this into an equation format, if you have a loading program like this, what Boltzmann superposition principle is saying that the total strain or the response is now going to be my individual responses summed. So, let us say you have the earlier you had delta sigma as the stress here, that is multiplied by J t minus tau 1. Okay. This is your creep compliance which is shifted now, so that the origin is at tau 1, and similarly you are going to add the other cases. and so on, right. If you generalize this idea, then you will realize, and you generalize this idea such that you go on making this smaller and smaller. So, these small time steps into smaller and smaller time steps, then basically you can have, you will have a set of rectangles that can approximate any particular signal, right. So, basically you are going to go from a discrete case to an integral case, right. That is what we are trying to do here. You are trying to take a system such that this delta sigma keeps going to 0 0, keeps becoming infinitely smaller, then what happens, right. So, then this generalization will get you to, so this generalization will get you here. Some people write it as minus infinity to t, some will write it as 0 minus, it depends on how you are so, this is now the generalization of this. And you can show that this form of the constitutive equation is actually, it's, so here you can replace minus infinity by minus 0 also, because what you, if we assume that there is no signal till t equal to 0 and at t equal to 0 there is a jump, then you can replace it with that. So, we see that this particular format of this equation, this is a consequence of a deeper principle, right, and that just comes simply from the idea of the step responses and the generalization of that. So, now, so what we are trying to do is we are trying to sort of conclude what we have in general learnt, and we are now in a position to write the summary of the various constitutive equations. Okay. So, in our case this goes actually from 0 minus. So, I will just put 0 here, minus 0, actually in that case actually just put minus 0 minus. So, what we saw is that this current state of stress can be written as an integral or tau, this s is a dummy variable inside, and this should be such that it is to be interpreted as, you can rewrite this entire thing as epsilon 0 g t plus 0 to t and you can just change using chain rule, you can change this to this form. Now, this is a convolution equation, and here you can actually just interchange the order of these and it will still remain unaffected, the integral, right. So, you can rewrite this entire thing as and then you can also switch these two here. So, instead of epsilon 0 multiplied by g t, you can make it g 0 multiplied by epsilon t and it will still remain the same. So, I will just write it here, you could just switch the order of this. So, similarly you will write it for the creeps, the creep compliance function, right. So, maybe I will just write one of them and then you can, so similarly you can write J T T minus S d sigma S, and you can derive this from, instead of the superposition of responses, you can either take first the input can either be the stress or the strain, right. So, the way you argue, you can get this, and this is going to be equal to sigma 0 j t plus 0 to t j t minus S sigma dot S ds. Yeah, and you can again switch the order of these or these, just like the previous case, right. Okay. So, we started off with a very simple case, the case of a very straightforward one single spring and a one single dashpot, either in series or in parallel, and we found two very straightforward some of the two of the simplest viscoelastic models, and then we built on and generalized it finally to get insights into viscoelastic behavior in a more general sense. Okay. So, we will stop here for today's lecture, and we will see you next time. Thank you.